Good morning everyone and welcome to today's worked exam answer video. Today I'm having a look at an aromatic chemistry AQA A-level question. So specifically thinking about benzene as our aromatic compound. We have got a 6-mark question today, and this is one of those levelled marked answers where the mark scheme will break down the chemistry content that you need to include into different stages, and in order to get either 5 or 6 marks you need to essentially cover all the points. You might get away with missing 1, possibly 2 if there's a lot of points, but yeah, essentially you need to give all the points in those 3 stages to get into the top level. So in this particular question they've broken it down into explaining the bonding, the shape and the stability, and the stability part is asked about quite a lot, and the stability part is relating to this hydrogenation data. So we've been given the hydrogenation data for cyclohexene and benzene, and we will be comparing what that tells us about the stability of benzene compared to Kekule's hypothetical cyclohexa 1,3,5-triene, which would be 3 double bonds inside of that hexagon, alternate single double bonds. So that is a fairly common question, usually worth 4 marks outside of, a particular level marked question like this. The extra parts that they've thrown in here to make it into a 6-mark levelled answer is the bonding and shape of the benzene molecule. Now, when I first looked at this question, I didn't include what I guess I considered to be points that were too basic when it comes to things like the bonding. So obviously you can't, for these 6 markers, write every single thing that you possibly know in relation to the topic, and that's not really what I'm getting at, but don't assume that something is too simple to say. When it says explain the bonding, talk about all of the components of the bonding, as you'll see when I go through it in a second. When it comes to comparing the stability of benzene, we're told to use the data in our answer, and any question like this that I've seen AQA produce so far wants you to use the data that they give you in your answer. So I'll talk through sort of where those marks come from, and in like a 4-mark question what those 4 marks would be for. Obviously we're not going to get 4 marks here just for talking about the stability of benzene, because we have to give at least 2 complete stages or 3 incomplete stages to get into a level 2, which will get us 3 or 4 marks, and that's where the levelled markers not catch people out, but you have to do more work to get the same marks that you would outside of a levelled marked question, which is not great, but there we are. Now, in terms of our presentation for this, the best thing to do is just break it down into the stages, and in certain questions like this one, it's a bit more obvious what those stages are going to be. So bonding first, then shape, then stability. Lots of the levelled markers, you can tell what the stages are going to be in the mark scheme. There are occasions where you can't, but please just try and be logical in what you're saying. They're going to be looking for you to not be jumping back and forth between points you've already made, and you've got to make sure that you've got your terminology correct and that it reads kind of well. It's not an English exam, but it needs to make sense. We can't be using keywords incorrectly, and we shouldn't be jumping about, which is why if you can spot what the stages are, you can kind of go, right, first I'm going to address the bonding, little paragraph, then I'm going to address the shape, little paragraph, then I'm going to address the stability, little paragraph. Now, there was a whole nother page of just lines for you to write on, so that's not the only space you've got. Now, I purposefully only printed this out so I could keep it on one piece of paper, but also to show that it's not how much you write. Obviously, you've got to include all the key points, but you can do that concisely and succinctly, and probably more effectively than kind of waffling on and writing loads and contradicting yourself and you know, jumping back and forth. So just take a moment before you start a 6 marker to kind of think, right, I'm going to do this, then this, then this. You don't need to plan it massively more than that, but just give yourself an idea of what you're going to talk about in each part of your answer, and what you think the key things are to include. So starting with the bonding, like I say, let's not assume that the examiner thinks we know anything. So the bonding inside benzene, that's the skeletal version, and we kind of have to draw the skeletal version of benzene because I'm not sure how we would represent the ring of delocalized electrons in a displayed formula. But we have to remember, therefore, that on each of these carbon atoms there is 1 hydrogen, just like in this cyclohexane structure. Every carbon is bonded to 2 hydrogens. We never show the carbon-hydrogen bonds in skeletal formula, but that is something that is there. So we have, in terms of the bonding, we have got 6 carbon-to-carbon bonds and 6 carbon-to-hydrogen bonds. These are all covalent bonds. Again, probably need to state that. It's not too simple a thing to say. The other thing that we can mention here is the bond lengths, because we have carbon-carbon single bonds, but and we don't have 6. No, we do have 6 carbon-to-carbon bonds. Sorry, I was questioning myself then. But they're not actually carbon-carbon single bonds. I know that's kind of how we've represented them on the skeletal formula. You know, we haven't drawn the 2 parallel lines to represent double bonds, but the CC bonds are actually intermediate in length between a carbon-carbon single bond and a carbon-carbon double bond. And that was one of the key pieces of evidence that disproved this cyclohexa 135 triene structure that AQA A first proposed for the structure of benzene. So let me add that in. So all covalent bonds, the 6 CC bonds are all equal in length, which is in between the length of a single and double C carbon-to-carbon bond. So that's definitely something that's important to mention when it comes to the bonding. So we've got the carbon-carbon bonds, got 6 carbon-to-hydrogen bonds, and again we might want to specify therefore that each carbon is only bonded to 1 hydrogen. I'll put that in now because we also, when we're thinking about the bonding, need to talk about the delocalized ring of electrons as well. So each carbon bonded to only 1 hydrogen, meaning each carbon has a delocalized electron. And then due to overlap of the p orbitals, these electrons form a delocalized ring. And that's also going to help us later on, because when we're thinking about the stability of benzene in comparison with this structure, the stability comes from having that delocalized ring of electrons. So that's a good thing that we've put in there in terms of the bonding. There's nothing to say that we have to answer this, bonding, then shape, then stability. You can answer it in any order you want to, so long as the stages are clearly addressed and not all muddled together. So you might think, well, stability of benzene might be best to do now. I'm just going to do them in the order that they are in the question, but like I say, any order for the stages is fine. In this case, obviously, if you're outlining a method, you need to do the method in order, so it won't always be the case you can do them in any order, but in this one you probably could. Now, in terms of the shape, there really isn't a right lot to say about this. It's a hexagon shape, so it's hexagonal. It's planar, so it's flat. All of the bonds are in the same plane. And that's it. So all I'm going to write for shape is a hexagonal, planar molecule. I'm not sure we'd need this, but it feels a bit wrong just to write 3 words. The molecular formula of benzene is C6H6, so that shows why it's hexagonal and why it's planar, because each carbon's only bonded to 2 other carbons and 1 hydrogen. So if it was a tetrahedral shape around each carbon, like it is for cyclohexane, if these bonds to the carbons are in the plane of the paper, we'd have 1 hydrogen coming out towards us and 1 hydrogen going back into the paper away from us. We don't have that with benzene because we only have each carbon bonded to 3 things, 2 other carbons and the 1 hydrogen. So that's why I've put that there. Okay, in terms of the stability part, let's assume that this is now a 4-mark question, just asking us about the stability of benzene and comparing that to the hypothetical cyclohexa 135 triene. That's the AQA A structure. So I guess the first thing that would be useful for us to do is maybe draw that out, keep the double bond there in the same place it is in the question, and then if that's carbon 1, 2, 3, 4, 5, 6, that would be our cyclohexa 135 triene, and that is the structure that AQA A proposed. The bond lengths were one of the pieces of evidence that disproved him. Another was the fact that benzene didn't react with bromine water in the same way an alkene would. We would expect to see, if it had 3 double bonds, the bromine water go from orange to colourless. We didn't see that. Benzene doesn't undergo addition reactions, and that again comes back to this delocalised ring. And then the third piece of evidence was the enthalpy of hydrogenation data, which is what we've got here. Now, we've only been given the hydrogenation data for breaking 1 carbon-carbon double bond open with 1 molecule of hydrogen to turn that into a single bond. So the first thing that we need to do to be able to compare the stability of benzene with the cyclohexa 135 triene is think, okay, if I therefore have 3 double bonds and I need 3 molecules of hydrogen to open up those double bonds to make them all single bonds, then this value will become minus 360 kilojoules per mole. Benzene is not minus 360 kilojoules per mole. Benzene is minus 208 kilojoules per mole. So benzene clearly was not cyclohexa 135 triene, and eventually they were able to come up with the delocalization model that we know of today. In terms of using the data in our answer, we've done the first bit, and you would get a mark for doing that on the diagram, so I'm not going to write that into my answer. But the second way we can use the data is to say how different benzene is to what we were expecting it to be. So there's a difference of 152 kilojoules per mole, and the reaction involving benzene is less exothermic, so that would be 2 marks. The third point is for saying it's less exothermic because benzene's more stable, and it's more stable because of, for the 4th mark, the ring of delocalized electrons, the delocalization model. Now, why does a less exothermic value show that benzene's more stable? I know that this is something that I had to get my head around when I first started teaching this a long time ago now, and this is something that I share with students to try and help them understand why a less exothermic value means that benzene is more stable. If we have a look at the product here, we're forming cyclohexane in both cases, and if we were to think about the amount of energy going in and the amount of energy being given out when these new bonds are formed as giving us our enthalpy change value, the amount of energy that's going to be released when these bonds are formed is going to be the same for both the cyclohexa 135 triene and the reaction with benzene, because we're making the same product. So if we were to break this down into its individual atoms and then put all those individual atoms together, the same amount of energy will be given out here and here. So if there's a smaller net release of energy with benzene, that shows us that more energy has to be going in to break down the original benzene structure than was used to break down this hypothetical structure. That's the only way that we can have a less exothermic value, if the exothermic component of the reaction stays the same. So hopefully that makes sense. Now, you wouldn't have to refer to that. That's more for you and your understanding of why that value is less exothermic. If anybody's not sure about that, please let me know and I can explain that again. So what I'm going to write for my remaining part of this answer is benzene produced, don't know what word to use then, my English isn't great, sorry. Benzene produced a less exothermic enthalpy of hydrogenation value. And then I'll use the data, so 152 kilojoules per mole less energy was released. This shows benzene was more stable than they expected. And this is a result of the ring of delocalized electrons. So if that was a question on its own, 1 mark for timesing that by 3, the 1 minus 120 to get minus 360, 1 mark for saying benzene's less exothermic by the 152 kilojoules per mole, 1 for saying it shows that benzene's more stable, and 1 for linking that to the ring of delocalized electrons. We've already talked about how those ring of delocalized electrons form, so I don't need to mention that again here. If I hadn't talked about it in so much detail there, I would have included it here, but there's nothing more that I need to say. Job done. So yeah, that would be our 4 marks on a 4 mark question. Here it's going to complete one of the stages on the mark scheme. Hexagonal planar molecule will fill the second stage in the answer, and then the bonding, how we've got 6 carbon-carbon bonds, 6 carbon-hydrogen bonds, they're all covalent bonds, all the bonds are equal in length. Having the delocalized electron per carbon, which becomes the delocalized ring, will be the final stage. So I probably wouldn't have wrote the first few sentences quite so kind of bullet pointy in an exam, but the rest of it I would have written exactly like that. So it shows, even though there was another whole line of paper, don't be worried if you don't fill all of the lines, okay? It's not an expectation that you fill all of them, and as I said, if you write more, you're more likely to kind of double back on yourself, which is going to make your answer less clear, less logical, less flowy. and you're more likely to contradict yourself or use keywords incorrectly. So the more concise you can be, the better, while still including all of those key points. As always, guys, any questions, please hit me up in the comments or drop me an email at missgtutoringandresources@outlook.com. Thank you so much for watching, and I will see you again soon.